lựa chọn một cái bài báo, các bạn tự trao đổi lẫn nhau, các bạn cùng đánh giá, các bạn cùng thảo luận để xem là nó liên kết với cái phần 1 của các bạn như thế nào, các bạn thấy nó interest hay không, và cái ứng dụng trong cái lĩnh vực hàng không của các bạn như thế nào. Đấy, thì cái đấy là cái bước mà tôi expect là các bạn sẽ thảo luận lẫn nhau, cùng trao đổi để chọn ra một cái bài báo mà các bạn thấy là nó phù hợp nhất với nhóm của các bạn. Thế tuy nhiên là mỗi người sẽ có một cái ý hiểu khác nhau, đúng không ạ? Đành rằng chúng ta thống nhất, nhưng mà mỗi người sẽ có ý hiểu khác nhau, mỗi người sẽ có một cách trình bày khác nhau, và diễn đạt vấn đề nó cũng sẽ khác nhau luôn. Thì tôi yêu cầu các bạn là trong một quá trình mà các bạn diễn đạt lại vào trong cái quyển tiểu luận của các bạn ấy, thì các bạn dùng chính giọng văn của các bạn để các bạn trình bày ý hiểu, tổng hợp lại, và chúng ta viết lại thành cái bài của chúng ta, và tôi chấm cái đó để xem các bạn hiểu như thế nào. Và tôi có hỏi các bạn thì cũng chỉ hỏi xoay quanh cái vấn đề là cái bài báo các bạn tổng hợp các bạn hiểu đến đâu, được chưa ạ? Và thực sự ra mà nói thì để hiểu một cái bài báo mà lại không phải là tác giả của bài báo thì nó cũng không dễ đâu. Các bạn hoàn toàn có một cái option là viết thư trực tiếp đến cho cái tác giả bài báo, cái corresponding author, để các bạn trao đổi, nhưng mà thường có lẽ là nó cũng hơi khó, nhưng mà đấy là một cái option cho các bạn. Nếu như các bạn đủ interest, các bạn hoàn toàn có thể viết thư cho họ để các bạn hỏi. Tôi là sinh viên đến từ trường đại học này, chúng tôi đọc thấy chúng tôi rất là interest. Hiện tại thì chúng tôi quan tâm đến cái vấn đề này và chúng tôi chưa được clear, thì đề nghị quý tác giả có thể giải thích rõ cho chúng tôi được không. Thì các bạn phải expect là 80% khả năng là người ta sẽ không viết thư trả lời, và 20% có khả năng người ta sẽ trả lời các bạn. Ngoài ra thì đó, các bạn có thể đọc thêm các cái tài liệu tham khảo, thì từ các cái báo review này, từ các cái sách giáo trình này, thì các bạn hiểu được cái kiến thức nền, để từ đó đọc báo của người ta nó sẽ dễ hiểu hơn. Thế thôi, không có gì đặc biệt cả.
Thầy với lại cho em hỏi xíu nữa là mấy cái vật liệu mà để người ta sử dụng cho mấy cái phương pháp đó thầy, có người ta ví dụ như là powder bed fusion đó thầy, thì có một số mấy cái loại bột mà ở đằng sau người ta ghi cái chữ là gray đó thầy, ví dụ như
Gray
là
nghĩa là sáng.
không phải thầy, cái chữ để em ghi cái ví dụ đó đây. Titan. Cái chữ đó này.
Graphite. Ok, graphite. Nó giống như là cái điểm của các bạn á. Thì cái anh titanium aluminum 64 này là một cái loại vật liệu khá là nổi tiếng, mà có thể dùng được cả trong lĩnh vực hàng không lẫn trong lĩnh vực y học. Thì cái titanium graphite ở đây thì nó sẽ liên quan đến cái thành phần hóa học ở trong đó. Nó là một cái dạng cụ thể, nó là một cái mark, nó giống như mark thép chẳng hạn. Đấy, thì nhìn vào cái mark đấy thì người ta sẽ biết là cái thành phần hóa học trong đó thì ngoài, tôi lấy ví dụ là trong titanium thì ngoài là 6% aluminum này, 4% vanadium này, titan này, thì cái quá trình tổng hợp nó như thế nào, quá trình nấu luyện ra nó như thế nào, thì nó thể hiện sơ bộ ở cái phần tên titanium aluminum 64 graphite. Thì nó sẽ khác so với cái grade 4, grade 3 chẳng hạn. Đó, thì cái này là
kiểu
một cái tên,
từng cái là nó sẽ phù hợp với lại từng loại ứng dụng luôn hay sao này?
Đúng rồi. Thì các bạn có thể xem ở chương titanium, ở trong vật liệu hàng không. Thì bạn đợi tôi một chút, bởi vì cái này thì trong sách của giáo sư Stefano Gianella của trường đại học Trento chẳng hạn, thì giáo sư có liệt kê một số hồi master thì tôi có học thầy Gianella, thầy chuyên về aerospace material. Thì thầy có tổng hợp một cái vài dạng vật liệu ở đó. Bạn đợi tôi một chút. Where is it? PDF lectures. PDF file. Chapter 3, as I remember. Just a little bit. Here. Daniel. Just a moment. I will show you. Ok, tôi sẽ trình chiếu cho bạn xem. Cái này thì bạn chỉ cần đọc lại trong cái kiến thức của vật liệu là bạn có thể thấy được. Thế thì các bạn có thể thấy này, đối với cái dạng là alpha type titanium alloy chẳng hạn, thì các bạn có rất thì cái grade, đúng không ạ? Thì đối với cái grade 5 thì ở đây người ta lại không thấy thể hiện. Thế nhưng mà tôi muốn nói cho các bạn biết là ví dụ grade 1, grade 2, grade 3 thì các bạn thấy các cái thành phần đi theo đó, đúng không ạ? Những cái mà được gọi là commercial poor titanium CP chẳng hạn. Đấy. Thì tất nhiên là các cái grade này để cho các bạn thấy là nó sẽ khác nhau ở cái thành phần, cũng như là cái ở đây cụ thể là gì. Đối với titanium thì người ta không expect trong đó là có thép, có sắt với cả oxygen đâu. Thế cho nên là cái này nó giống như kiểu là cái giới hạn thép với cả oxygen được phép có trong cái alpha grade 1 này của titanium. Đó. Thì để nói lên là gì, tôi canh nấu luyện ra cái loại vật liệu đấy như thế nào tôi không biết, tôi chỉ cần biết là đến cuối cùng cái chất lượng nó phải đạt được như vậy, thì đó là cái mark của nó thôi. Người ta nhìn vào để người ta phân biệt các loại titanium khác nhau, cùng là aluminum, titanium aluminum 64 chẳng hạn, nhưng mà cái việc tạo ra nó sẽ khác nhau, cái chất lượng nó cũng sẽ khác nhau, cái cơ tính rõ ràng nó sẽ khác nhau. Đó, nó liên quan đến cái thành phần ở trong đó. Đúng không? Thì các bạn thấy này, titanium aluminum 64 chẳng hạn, TE64 chẳng hạn, thì nó chính là viết tắt của titanium aluminum 64. Okay, so now I would like to introduce to you about 4 different type of sintering mechanism for AM, but I would like to focus only on solid state sintering. Yes, for the others you can read them at home. For the solid state sintering, is actually the fusion process for powders, but without meltings. It just locally melt the contact region between the particles. At elevated temperatures, and the temperature is normally around half of the melting temperatures of the materials that's subject to the sintering process. And the driving force for the sintering process is to minimize the free energies. It's actually the surface energies. So the surface energy is related to the surface area of the particles. So in order to minimize the surface energies, you need to minimize the area of surface. This can be done. So for example, if you see from the figure A here, you see that, okay, the more particles you have, the higher amount of areas, surface area you could have. Yes, in order to minimize the surface area, you need to join the particles together to form a neck, and therefore the surface areas can be reduced. This is a driving force. This is the reason that the sintering can be occurred. And when the surface particle surface area is reduced, and then you reduce the driving force. I mean that once the sintering process occurs for a certain period of time, the neck is formed, and therefore the surface area is reduced, and then the rate for sintering is reduced. And if you want to increase the sintering, and you need to increase the sintering time in order to promote the sintering process. Yes. Or you can also apply the higher temperatures in order to, how can I say, promote the density, the sintering process, to improve the density. The surface area is the function of the particle size. So the smaller the particle, and the higher the driving force you should have. Yes, for create the neck and for the consolidation. And if you have the small particles, in other words, you would have the faster sintering process. And the sintering can be initiated at lower temperatures comparing to the case of larger particles. Increasing the temperatures, you can increase the diffusion rate, because in that case you provide more free give energies to atoms to diffuse, and therefore you can improve the diffusion rate. And as a result, the sintering can be performed rapidly. Yes, especially if the temperatures approaching the melting temperatures, because you see that basically in a normal situation we just expect the temperatures of sintering which is equal to 1/2 of the melting temperatures. But if in the case of increasing sintering temperatures up to the melting temperatures, and then yeah, it's not the case that we expect. Yes, because at the temperatures, at these temperatures, I mean the melting temperatures, the diffusion induced solid state sintering is the slowest mechanism for Patabeth fusion technologies. So please refer to these parameters, the sintering temperatures and the particle size, because you know that reducing the size of the particles, we have a higher driving force for sintering process, so we can promote the sintering at faster rate and lower temperatures, which means that you save energy for the sintering process. For the additive manufacturing, so you can save time in order to form a layer. So this is an issue of enhancing economic competition. Yeah. So in order to how can I say, enhance the economic competition, the heat source is mean that the laser, the electron beam, or the plasma arc should move. I'm sorry, just the laser or the electron beam should move quickly as possible to quickly induce the fusion. So in other words, you can enhance the building rate. And there are actually three ways that the sintering can affect a building process for additive manufacturing. So for example, at elevated temperatures, and then the you use the heat source in order to irradiate onto the specific area defined by slicing process. But since the metal powders have the thermal conduction properties, is thermoconductive, so the heat can be transferred to the surrounding area, and the powder bed surrounding can also sinter. Yeah, you know that. It means that the powder bed. So we irradiate the laser to a specific area, to the cross section, to sinter the powders within the cross sections. But at the same time, seeing the metal powders are thermoconductive, electrical conductive as well, yes, but thermoconductive, and therefore the heat will be transferred to the surrounding area. That the surrounding area, the powder bed surrounding, also sintered. Yeah, and 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 if this happens, this means that the spreading process can be changed. Yes, and this affects also the melting characteristic. Yes, however, it also has the positive effect. Yes, because it's enhanced the strength of the surrounding powders and help to reduce the part curling or the part distortion. If melting, this means that if the surrounding powder is sintering, so you have the first point. If the surrounding powder is melt because the cross section is hot, yeah, and if you have sufficient time of a heat transferring process, yeah, and and a skin can be grow on the outer surface of the part. This means that an an additional amount of powders will attack to the surface of the part after the additive manufacturing process. This means that there is a skin will be grow on the design, and you have to eliminate the additional skin. And this can be solved by offsetting a laser beam to compensate the part growth. Or you use the milling process to eliminate, yeah, the skin, the extra skin, and that's all. Offsetting the laser so that the heat transfer to the surrounding area is not so yeah, is not so far, or is reach the surface which is actually the design surface for the part, and that's all. Do not offset too close to the design scale, and that's all. The other is you post machining process to eliminate an additional skin, and that's okay. Rapid fusion of parabet by heat sources, because it's move fastly for the laser, for the electron beam, for example. So it's hard to achieve 100% dense materials due to the distribution of the porosity. And we know that the voids inside the material is the area that the stress is concentrated, and therefore when the part is subject to the cycling load, and the crack can occur at the stress concentration area. And if the crack is growth, it means that the crack can be propagated into the solid material, and finally we have fracture, and then it should be avoided. I mean, we should achieve we should produce the parts with 100% relative density. And if it's not, and then the voice is detrimental to properties or mechanical properties of the materials. And therefore, if the metal parts is printed at high enough temperatures to be able to promote the diffusion and grain growth, and part can reach 100% density. But it's just the density, because you know that at high temperatures, the diffusion process occur fastly, and the grain growth. Grain growth is mean that we within a specific volume, the grain grow, and the number of grains is reduced, are reduced, or the number of grain is reduced, and therefore the grain boundary region will be reduced, and you would have the weaker materials, because you need to reduce the size of the grain in order to improve mechanical properties of the materials, as I already mentioned. Yes, concerning three different sintering or melting mechanism remaining for AM, like the chemical induced sintering, or liquid phase sintering, or liquid partially melting. So you can read them at home. So there's no special thing. Solidification and microstructure. So in material science and engineering, it is quite important to investigate the relation between the processing parameters, microstructures, properties, and performance of the materials. And the solidification and microstructure will have the special influence on the final properties of the synthesized material or additive manufactured materials. And most additive manufacturing method process are based on fusion. So melting, coalescence, and solidification. And you know that with the additive manufacturing deposition, so we deposit material layer by layer. Yes. And the process has repetitive and directionally dependent effects. In other words, properties of the material in different direction will be different. In other words, we call anisotropic properties. Yes, we prefer that the material has isotropic properties, which means properties in different direction are the same or similar. But here we have anisotropic, so this is unexpected. We have rapid solidification, for the additive manufacturing process. The cooling rate range is generally quite fast, from 10 to 3 up to 10 to 5 degrees C per second, result in the so-called refined microstructure. So because the cooling rate is so fast, and then the microstructure is refined, or is fine. Yeah, it's fine. So small grains, because it's cooling so fast that the grain cannot be grow. The cooling rate is fast, means that the temperatures inside the material is low, and then the material or the atoms is not receive enough free give energies to diffuse for the small grain size. In other words, you have the refined microstructures. Yeah, and you have because you have the very fast cooling rate, and therefore you would have the metastable phase, like in the case of a magnesite, when it's transformed from the austenite structures, and then you have the metastable phase like martensite, and then you need to perform some kind of heat treatment to bring back to the more stable one. The microstructure evolution depending on manufacturing factors. For example, the peak temperatures, the cooling rate, because the cooling rate will have the certain effect on the size of the grain, whether or not we have the segregation of the constituents, sorry, the phase fraction, yeah, and so on. The reaction kinetic, yeah, cái động học của phản ứng, reaction kinetic, and therefore you have yeah, different type of crystallographic phase structures. And in additive manufacturing, we may have we can have the melt back from the bed of the previous layer, and therefore grains can continue the grain orientation of the previous layers. And the fact is that many additive manufacturers, the problem is that we want to reduce the effect of anisotropy, yeah, and therefore they randomize the deposition part. Because if just covering like this, so for sure the properties in the horizontal direction and vertical direction will be absolutely that different, and therefore they randomize the scanning part, yes, the strategy of the scanning process in order to minimize the effect of anisotropic properties, and therefore they can minimize the stress concentration, the wrapping process of bulk materials. This is an issue of additive manufacturing because the properties of the material is anisotropies. Comparing the case of casting or forgings, where uh, we expect that the material behave more isotropic properties or possess more isotropic properties. And in terms of the solidification process, it means that we cool down the material from the molten phase to the solid phase. The defects, the microstructure defects can alter, including, for example, the segregation, the hot cracking. Hot cracking where we have yeah, fast cooling rate, because we have fast cooling rate. The grain growth, yeah, in some cases, and undesirable phase transformation, yeah, or formations, yeah, can form during this process. Or if the heat source provide more than enough energies to to sinter or to melt the materials, this means that you provide too much energy to sintering process, and then the material can be vaporized, bốc hơi, and therefore you loss of alloying elements, and the properties will be modified because you lost elements. The composition is already modified, and this is unexpected as well. The additive manufacturing can be combined with other processing steps like forging or other kind of heat treatment to improve properties of the materials. So you can combine with forging, you can combine with annealing, solutionizing, homogenization, and recrystallizations. Or pH, yes, I have already mentioned to you about the precipitation hardening, tạo ra các cái pha rán nhỏ bị phân tán, maybe used in metal EM as the post-processing step in order to improve properties of the additive manufactured materials. The hot isostatic pressing, yes, I already mentioned as well, involving the application of high temperatures, high pressure to consolidate the powder, to close pore, to heal the defect inside the materials. And to a certain extent, hot isostatic pressing can reduce anisotropic properties of the additive manufactured materials. But again, you you must keep in mind that is relatively costly and size limitation, because you have to put the part inside the oven. Yes, and the size of the part which can be treated by hot isostatic pressing cannot be large. And you can see the video regarding the hot isostatic pressing for powder metallurgies at home if you want. And you also have the ultrasonic consolidation. Is the variation of AM process, but I would not like to focus here. And one of the issues that you could see from the figure on the right side of this line is whether or not there's a presence of the certain amount of oxygen inside the building chamber. And if you have this smaller than 50 part per million oxygen, so the oxidation reaction is occur limitedly. And if, yeah, I'm sorry, yes, yeah, fine. Uh, if it's 5% of oxygen, you can see that how the oxidation reaction occur inside the building chambers. And in that case, a lot of slack can be performed, which significantly modify the properties of the material after the process. And you would have also an unexpected phase, yeah, after the synthesizing process, and this should be avoided. This should be avoided. This is why we should use the shielding gas. We should control the environment inside the building chamber by limiting the amount of oxygen, nitrogen, hydrogen as well inside the building chamber to guarantee specific qualities of the materials. And you can see that if you limit the amount of oxygen, which is around 5 part per million, so the porosity inside the material is quite limited. But if it's 3,000 part per million, and then the porosity is significantly enhanced. Mhm. And it also depends on the not only on the oxygen but also on the moisture, yeah, the water gas inside the building chamber as well. And again, the environment inside the building chamber must be controlled, yeah, in order to guarantee a specific qualities of the materials. There are different forms of metal. Commercially, yeah, the metal have a different kind of shape, like the sheet metal, plate, pipe, and tube. Yeah, the angle iron, like you use for creating the shell, or the I-beam when you need to, how can I say, create the ceiling of the of an apartment, for example. AM metal machines rely on the metal powders and wire. So they are the two most commonly used uh, feedstock material forms in order to fabricate the part. So for example, powder bed fusion use powders as feedstock materials, like direct energy deposition can use wire, and both wire and powders. Both wire and powders. Okay. So I would not like to concentrate on table, but you can see that for direct energy deposition, you can use powders, wire. For powder bed fusion, of course, seen is already included in the name of the technologies. So we can already use powder as feedstock material. So nomenclatures, nothing special. Power, speed. You see that the speed, scanning speed is relatively high. And since for example, butterfly fusion must be performed within the building chamber in a controlled environment, and then the size of the building chamber is smaller comparing to the cases are the cases of direct energy deposition. However, in the case of dimensional accuracies, and Butterfly fusion has higher accuracy, or in other words, the part which is made of Butterfly fusion has higher accuracy comparing to those which are made of direct energy deposition. And the higher accuracy means that you need less step for post processing. Yeah. Yes, and some common metal types, so which means that some common material that can be used for AM. It's not the form, but is in fact the material that we are considering for the moment. For example, for using in additive manufacturing area, we can use aluminum. Yes, aluminum can be employed in prototyping, aerospace industry, yeah, to fabricate different parts for aerospace industry, for automotive industry, or other consumer products. Yeah, because we can customize the product. So the customer can select the materials and ask the uh, how can I say service company to fabricate the parts upon their request. But again, still, yeah, we can use to fabricate the, for example, decasting mold or injection mold or different kinds of tooling. This is high strength, has good corrosion and wear resistant. So it can be used for the tooling materials. Stainless steel, yes, for sure. It can be used for a wide range of applications, from the medical devices, food processing, pharmaceutical, aerospace, or another types of products. Nickel-based superalloys for sure can be used in 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 the jet engine or in the engine of the airplane. In specifically in Conan 625 and 718, because of the fact that they behave good grip and tensile strength at relatively high temperatures, above 600 degrees C for sure, and typically work at they work at 800 degrees C, more than 800 degrees C. Good machining and wettability, so therefore is compatible with additive manufacturing because it's based on the wetting process. So nickel-based superalloys can be widely used in aerospace applications, as I already mentioned, in aero engine or combustion chamber, because it can work at high temperatures. But if you need the high ability of heat resistant, and then you need to coat the nickel-based alloy parts with thermal barrier coating in order to enhance uh, the ability to withstand heat. Titanium alloy, yes, titanium aluminum 6 is quite common. Yeah. For aerospace or for medical application. Cobalt chromium alloy, yeah, I did not work with these alloys previously. Generally speaking, is biocompatible. This can be used for medical and dental application, but can also be used for aerospace application because of the fact that it possess good strength, especially at high temperatures. Yes, interestingly, refractory metals can also be used for fabricating parts by additive manufacturing, like tungsten, molybdenum, niobium, tantalum. Yes, but since this material has very high melting temperatures, so we do not use, for example, laser sintering or direct energy deposition in order to yeah, to bind them together. Instead, they use the by the zetting technique, yes, to fabricate the part without melting. Because you see, the melting temperatures at tantalum, niobium, and molybdenum, yes, is quite they are quite high. quite high. Yeah. There are 4 ways of producing powders. Yes, above we are talking about the different types of material. Below we are talking about the form of the material that can be used, in specifically the powders. And there are 4 ways to produce powders, including gas atomization, rotary atomization, and plasma rotation electrode process, and others. But yes, and C here is corresponding to the figure on the right side. Yeah, A here, E here, and so on. Yeah. And depending on the technologies that can be used to fabricate the powders, you may receive different kind of shape of powders. So for example, with A, plasma rotating electrode process, you have a spherical shape, and the shape is regular. Yes. In the case of B, rotary atomizations, rotary, yes. So pouring molten alloy on the rotary disc, and therefore is a little bit long comparing to the case of a spherical shape in the first iteration, and so on. But try to avoid the case of E, because when you pack them together and the porosity in between particle uh, is high, and then it's quite hard to achieve dense part. Yes, because it has the powders have irregular shape, and then to be honest, quite difficult to pack them together to consolidate and form 100% part. Yes, it's quite hard to do that. Right. Yeah. So here we can talk about the processing parameters. Mhm. uh, that can be used to fabricate several types of stainless steel by additive manufacturing. So most of them, for example, we will pay more attention to the 316L stainless steel. We consider about the power, the scanning velocity, and the hitch. The density can approaching 100%. That's not always possible. There are 2 orientations that they consider: the longitudinal and transversal directions. And you can see that scene additive manufacturing, scene we produce the part layer by layer. And therefore additive manufacturing part has anisotropic properties, which means that the hinge strength in different direction, in the longitudinal direction and in transversal direction, are different. And therefore you could see that you have 2 values of hinge strength in 2 different directions. Yes, there's an evidence showing that, yeah, the properties of the additive manufacturing part are anisotropic. Mhm. Yes, and and the first table showing you the technologies that can be used to fabricate the steam parts is direct energy deposition. The second one is by Patabet fusion. Yes. Yeah. And to be honest, depending on the machines and other type of parameters that you have selected for manufacturing process, you have the relatively large deviation of the values regarding the hinge strength, ultimate strength, or percentage of elongation, as well as the hardness. Here is the Vicky hardness of the material, how can I say, the additive manufactured materials. Similarly, you have different type of parts. Yeah. made by different technologies with the same feedstock material, titanium aluminum 64. I would say the same, but it's not. They are not actually the same, because the name is titanium aluminum 64, but the condition can be different. So that after the manufacturing process, you will have different actually materials. Các bạn có hiểu không ạ? Cái vấn đề ở đây là mặc dù là cái điều kiện đầu vào của chúng ta vẫn là cái bột kim loại titanium aluminum 64 chẳng hạn, tuy nhiên là với cái thông số của quá trình gia công vật liệu nó khác nhau, dẫn tới là sau cái quá trình gia công đấy thì tính chất của vật liệu khác nhau, và cứ mỗi tính chất thì nó sẽ tạo ra một loại vật liệu khác nhau. Mặc dù là các anh đầu vào giống nhau, nhưng mà sinh ra thì hầu hết các anh đấy cơ tính khác nhau, là các loại khác nhau luôn, đúng không ạ? Tôi lấy ví dụ là vì cái điều kiện tổng hợp nó có lẫn oxygen chẳng hạn, lập tức cơ tính sau đó nó thay đổi, thì cái loại đó nó lại thành cái anh khác rồi, bởi vì cái thành phẩm sau đó nó sẽ chứa rất là nhiều những cái thành phẩm bị oxy hóa, đúng không ạ? Porosity nó cũng sẽ bị nâng cao lên, cái tính chất sẽ bị giảm đi so với trường hợp mà chúng ta control được cái lượng oxygen ở trong cái phạm vi tiêu chuẩn, thì dẫn tới là chúng ta tạo ra hai cái loại vật liệu khác nhau, mặc dù cái anh feedstock material đều là titanium aluminum 64. Thì gọi nó là khác nhau trên cái góc nhìn như vậy. Yeah. And here we consider the fabrication of titanium aluminum 64 with different techniques. So for example, butterback fusion using laser as heat source, or butterback fusion using electron beam as heat source, or the direct energy deposition. So we would have with different techniques to fabricate the part with the same, for example, feedstock material, and you would expect to have different properties. Yes. It depends on the technology that you use to synthesize the materials, and it also depends on, let's say, the parameters, the processing parameters to synthesize the materials. Yeah. In terms of metal powders, we pay more attention to those factors like the size of the powder, shape of the powders, the chemistry or the composition of the powders, because they are the critical factors for a successful process regarding additive manufacturing. Because you know that the issue is that after the additive manufacturing process, you must fabricate the part successfully. You should have the part with high relative density. So in ideal case, 100%. The part should have the shape which is close to the finer shape. Close to the shape of the final products. Yes, and we can control the composition of the part after the additive manufacturing process. This means that we must prevent or reduce some kind of oxidation reactions, yeah, and so on. The conventional metal powders can be produced by water atomizations, and you should have you can have different shapes accordingly, yeah, alternatively. Yes, the shape can be angular, can be irregular. Yes, we do not want to have irregular shape of the powders. Or agglomerated có nghĩa là một cái cụm dính kết của các cái powders. Chúng ta muốn là các cái powders nó phải tách nhau ra, nó phải có hình dáng giống nhau và tròn đều, đúng không ạ? Có kích thước phân bố trong một cái khoảng hẹp thôi, có nghĩa là cái size của powder nó gần giống như nhau. Nhưng mà cái water atomization này thường thì sẽ không cho cái sản phẩm có chất lượng quá cao. Các bạn có thể nhìn thấy. And the size can range from the nanometer scale up to more than 100 micrometers or microns. The powders for additive manufacturing should have the size range in between 10 up to 105 microns. The material in front of the powders should have the spherical shape. Yes, because you see that on the slide number 7, we're talking about the driving force for the sintering. Yes, and we have 4 different powders coming to contact with each others. So we need the contact between different powders. So if the size, the shape can be controlled, yes, and then it's easier for the sintering process. Or easily spreading the fly layer powders, delivering the inert gas yeah, powder smoothly. So to prevent some kind of nozzle clogging, có nghĩa là nó bị ngăn cản, có nghĩa là hạn chế được các cái tình huống mà bị tắc ở cái vấn đề cái vòi, đúng không ạ? Cái vòi deposit cái vật liệu. Yeah, I suppose that I have speak too much information, so it's the reason that I drink water more frequent as easier than usual. Yeah, the size, shape, and chemical purity of the powders are different and may be optimized for AM process. I would say that should be optimized for AM process because, yeah, the better the input material and the better the uh, the quality of the part after the additive manufacturing process, for sure. It's not always, but the probabilities, the probabilities of number of the part which have the better quality should be higher. Xác suất xuất hiện những cái chi tiết, đúng không ạ, có tính chất tốt sẽ cao hơn là cái trường hợp mà chúng ta không optimize những cái tính chất của các cái powder trước khi chúng ta đưa vào cái quá trình tổng hợp bằng additive manufacturing. Powder sieving, có nghĩa là sàng powder, may be used for creating optimal range of powder size and removing irregular naked powder particles. So please keep in mind that during the powders production processes, for example. So it's starting from the metal pool or molten metals. So the metal will be ejected from a nozzle, and below the nozzle is a cooling environment, and then we should have the atomization process. So for any reasons that the powders can stack together, to form the agglomerations. So it will affect the spreading process to create the 5 layers for the powder bed fusion process. And in that case, the irregular powder or the agglomerations should be should be avoided or should be prevented by using the powder sieving to eliminate these large powders or the irregular shaped powder or the agglomerations before we subject the feedstock material to the fabrication process. Yeah. Okay. 1:49. So I think that we can stop for 10 minutes and then we can resume the class at 2.